In stats, we wrapped up chapter 6. We reviewed these properties. We talked about these before the winter break, and then we went on. But as review, binomial distribution has this acronym BINS, binary independent, fixed trials, success is constant. Geometric does not have fixed trials. Process continues until, keyword is until failure. Or it could be a matter of until success. All right. Back to binomial, there's the formula that's typed on your formula sheet. We're going to use binomial PDF when the question says x equals or exactly. We're going to use CDF when it's a less than or greater than. All right, so let's jump to just practicing one of these. It's been a while. So we have this scenario here about free lunch. This is actually a pretty cool deal. I wish a restaurant would do this. So it looks like when you walk up to pay, you push a button, and it draws a card from a standard deck. And if it's a 3, you win your lunch for free. So there are 4 3s in a deck. Probability of winning any one trial is 4 out of 52, which I like to convert it to a decimal, although you can type a fraction into the calculator when you do the binomial probability, but I like to have a decimal, so I'm going to use 0.769 for my probability of success. All right. Skimming through this, it is binomial because it resets for each person, and there are fixed trials, 12 people. No one person affects the next, so it's really important to write these 3 things. And then probability of x equals 2. So grab your calculator. You can just write the answer down at this point. That is plenty of work to just write the answer down. But I'm going to write it like this, so everyone knows what to type in. Or another way to write this is in formula notation. So that would be 12, choose 2. Probability of success is 0.769 raised to the second. And probability of failure raised to the 10th. Notice 2 and 10 add up to 12. So that probability is 1753. All right. If you need to see it on the calculator, you press Menu, Stats, Distributions, and Binomial PDF towards the bottom of your screen. So 12.0769 and 2. All right. Let's try another one. This time they up the sample size to 250 customers, but everything else is the same. They want to know, in this circumstance, what is the probability of fewer than 10? So since we have a less than, we need to use binomial CDF. N changes to 250. Success rate is the same. This time there's a lower and upper. So the lower would be 0, because there could be 0 wins. Or the upper needs to be 9, because it says fewer than 10. So what the calculator is about to do is do that whole binomial process that we wrote up there, that formula, 10 times, and it'll add each one up. And it does it in a heartbeat. Very nice. So when you do that, it is 0.0062. Very unlikely that it's going to be fewer than 10 people. All right. Binomial CDF, by the way, is right below PDF. Find it in the same spot. So go to distributions, and you got to scroll down. So there's PDF. We want CDF. All right. All right, moving on. I think that was the end of that one. We have 2 new formulas, and this is the only new thing we're really learning today, and that is the mean of a binomial distribution and standard deviation. So these are 2 shortcuts. This still works right here. If it's binomial, you can still do this one. But that one's pretty tedious, and this one is really tedious. So if it's just some discrete random variable and you don't know it's binomial, you use these 2. If it's binomial, this is a big time shortcut. All right? It totally depends on what type of variable it is. And we've seen both. I'm giving out a practice test today, and you can compare the 2. All right? So if it's just some discrete random variable, the big giveaway is it's not binary. There's many different possible results. Then you would use those 2 blue formulas I just wrote. But we're talking binomial right now. So let's review binomial. This is a water experiment, and I would say it's binary, because people are guessing which one is the bottled water. So they are right or wrong in their result. It's independent because, 21 students are doing this, and each student's guess has no effect on another student. Fixed trials. N equals 21. And success rate is constant. It's like they don't get better at guessing because they're only, let's change that, I'm talking and writing. There we go. So they're only guessing one time, so it's not like they're getting better with their guesses. So it's binomial. Find the mean and standard deviation. So let's practice that formula at the top of the screen. We have 21 people with a 1/3 rate. On average, 7 will guess correctly. For standard deviation, it's that square root formula, which is the expected times the complement. And you end up getting I believe it's 16. Yep. So we know on average, the correct guesses I guess I should say number of will be within 2.16 of the mean. I think there's one more question down here. And this is a hard concept right here. So no distribution characteristics change, still 21, still 1/3. And they see that 13, or they're curious, 13 made correct identifications. They're wondering if they're just guessing. So the way you approach this is you assume they guess, and to test significance, find the probability of the value that occurred which is 13, or anything more extreme. So that means I need to find the probability of x greater than or equal to 13. And that's just the rule of significance. It's this hypothesis concept where if 13 happened, now the question becomes, what was the likelihood of 13 or more occurring? All right, because we want to get this shaded region, this rejection region of whether or not they're guessing. So you jump to binomial CDF. You've already defined the distribution on part A, so you don't need to redefine it. But here's all the calculator speak if you need it. This time the lower is 13 and the upper is 21. And when you do that, you get a tiny probability. You get 0.0068. This is very unlikely to have happened, and yet it did happen. So this means evidence suggests students are not guessing. I think the bell's about to ring. And this is because 0.0068 is less than 0.05. So you need to answer the question. You need to use context and refer to the probability and whether it's small or big. So evidence suggests students are not guessing. Maybe I should say more context about which one is bottled. And you got it. All right. I believe that's the end. I know there were more in this packet, but that's as far as we're going to go for the test. So, see y'all later. Bye.